There's a photograph from Princeton, taken sometime in the early 1930s, of Einstein and me standing near the Institute, both of us looking slightly away from the camera. And every time I've seen it reprinted somewhere, I've thought the same thing. Nobody looking at that picture would guess that the two of us spent years quietly at odds over something neither of us could ever fully prove to the other. Not politics. Not the war. Not yet. Physics itself, the deepest question physics had ever asked. Whether the universe, at its most fundamental level, actually decides things, or whether it simply doesn't know the answer until you force it to. I want to tell you how that disagreement started because it didn't begin with an argument. It began with admiration. By the time I arrived in Europe as a young man to study, quantum mechanics was maybe 5 or 6 years old as a fully worked out theory, and it was already the most successful thing physics had ever produced. Heisenberg had built his matrix mechanics in 1925, sitting on a treeless island in the North Sea, trying to nurse himself through a bad case of hay fever. Schrödinger built an equivalent wave version the following year. Within a couple of years, the two formulations were shown to be mathematically identical, and the theory could predict the spectral lines of hydrogen, the behavior of electrons and metals, the structure of the periodic table, all of it with an accuracy that no theory before it had ever managed. I studied under Max Born and Göttingen, and I watched this new physics get built in real time, watched it work again and again in situations where the old physics simply had nothing to say, and I believed in it. Not the way you believe in a hypothesis you're testing, the way you believe in something you've watched prove itself too many times to doubt. But there was a strangeness sitting right at the center of the theory, and everyone who worked in it knew it was there, even if most of us learned to live with it. The equations of quantum mechanics don't tell you what a particle is doing, they tell you the probability of finding it doing one thing or another. Before you measure an electron's position, the theory doesn't say it has a position you simply don't know yet. It says the electron doesn't have a definite position at all. It exists as a spread of possibilities described by something called a wave function, and only the act of measurement forces one of those possibilities to become real. Born was the one who first proposed reading it that way, treating the wave function as a probability distribution rather than a description of some hidden deterministic reality underneath. Bohr, in Copenhagen, took that idea and pushed it further than almost anyone was comfortable with. He argued that asking what an electron is doing between measurements is not a hard question with an answer we haven't found yet. It's not a question physics is equipped to answer at all because there is no fact of the matter until a measurement happens. The particle isn't hiding a definite state from us. It doesn't have one. Heisenberg's uncertainty principle sat right underneath this. It's not simply a statement that our instruments are too crude to measure both a particle's position and its momentum precisely at the same time. It's a statement that a particle cannot possess a perfectly definite position and a perfectly definite momentum simultaneously. Not because we lack the technology, but because those two properties are, in the mathematical sense, incompatible with each other at the level of the wave function itself. The more precisely you pin down one, the less defined the other necessarily becomes. This wasn't an engineering limitation. It was, according to Bohr and Heisenberg, a fact about the structure of nature. Einstein could not accept it. And I want to be careful here because the popular version of this disagreement makes Einstein sound almost old-fashioned, a genius who simply couldn't keep up with the new physics he himself had helped create. That is not what was happening, and anyone who actually read his arguments closely the way I did knew better. Einstein had done as much as anyone alive to build quantum theory in the first place. His 1905 paper on the photoelectric effect, the one that actually won him the Nobel Prize, not relativity, was one of the founding acts of quantum physics. The paper that first proposed light itself comes in discrete packets of energy, he wasn't rejecting quantum mechanics as an outsider. He was objecting to it as one of its own architects. Someone who believed the theory, as brilliant as it was, could not be the final word. His objection came down to a single conviction. One, he stated to me directly, more than once, in different words each time, but always the same underlying thought. He could not believe that God plays dice with the universe. He didn't mean this as a religious statement. He meant it as a statement about what a complete physical theory ought to look like. A fundamental theory of reality, in his view, should describe what is actually happening, not merely the odds of various things happening. If quantum mechanics could only give you probabilities, Einstein's position was that the theory must be incomplete, that there had to be some deeper layer underneath it, some hidden variables we hadn't yet discovered. That would restore a fully deterministic picture of nature once we found them. I remember conversations with him where he'd walk me through a thought experiment, testing the theory's foundations the way you'd test whether a bridge could bear a load it wasn't designed for. He was relentless about it, and brilliant in a way that made you feel the floor shift slightly every time he spoke, even when you were certain he was wrong. The disagreement crystallized most sharply in 1935 in a paper Einstein wrote with two younger physicists, Boris Podolsky and Nathan Rosen. We called it the EPR paper after their three initials, and it remains, in my opinion, one of the most important papers quantum mechanics ever forced someone to write, precisely because it was trying to tear the theory down. The argument went like this. Imagine two particles that interact briefly and then separate, flying off in opposite directions, carrying correlated properties between them. What we'd later come to call entanglement, though that word wasn't yet standard at the time. According to quantum mechanics, neither particle has a definite value for a certain property, say its spin, until you measure it. But here's the strange part. The moment you measure the spin of one particle, you instantly know the spin of the other, no matter how far away it has traveled in the meantime. Miles away. Light years away in principle. Einstein's argument was elegant and, I'll admit, deeply unsettling the first time you sit with it properly. If measuring one particle instantly determines the state of a second particle far away, one of two things must be true. Either some influence is traveling between them faster than light, which would violate relativity, a theory Einstein trusted as much as anyone alive trusted anything, or the second particle already had a definite spin all along. One we simply didn't know until we measured the first particle. In other words, the properties were real and pre-existing, and quantum mechanics, by refusing to describe them, was simply an incomplete description of a deeper, more complete reality. He called this idea of pre-existing properties waiting to be revealed rather than created by measurement, elements of physical reality. And he argued that any complete theory needed to account for them directly. Bohr's response to EPR took him weeks to formulate properly, and when it came, it didn't refute the mathematics of the paper at all. It refused the framing underneath it. Bohr argued that the whole question of whether a particle has a property before you measure it is built on a classical intuition that simply doesn't survive contact with quantum reality. The two entangled particles, in his view, are not two separate systems that happen to be correlated. Until measured, they are described by a single unified quantum state, a single wave function covering both particles at once, regardless of the distance between them. There's no signal traveling from one to the other because there's no meaningful sense in which they were ever fully separate systems to begin with. Measuring one simply completes the description of a system that was never truly divided in the first place. I sat with both of these arguments for years, And I want to be honest with you about something. I never fully sided with either of them the way people sometimes assume I did. I respected Bohr enormously, more than almost anyone I ever studied under, and I understood better than most why his framework worked as well as it did. It made correct predictions every single time in every experiment anyone devised to test it. But I also understood exactly what bothered Einstein, because it bothered me too, quietly, in a way I didn't always say out loud in Bohr's presence. There was something deeply uncomfortable about a physical theory that seemed to say the universe genuinely doesn't decide certain facts about itself until an observer forces the issue. Not that we don't know, that there is nothing to know yet. Einstein and I disagreed, but not the way two strangers disagree. We disagreed the way two people do when they respect each other's minds too much to let the argument go. He would visit, or I would see him at the institute, and the conversation would circle back, almost involuntarily, to the same unresolved question, sometimes framed as physics, sometimes framed, in his case, almost as a matter of aesthetics, what a true theory of nature ought to feel like, ought to look like, on the page. I never fully agreed that hidden variables were waiting to be found. Everything I understood about the mathematics of quantum mechanics told me that Bohr's picture, strange as it was, described something real about how nature actually behaves at that scale, not merely a gap in our knowledge. But I never dismissed Einstein's discomfort either, because dismissing it felt like a kind of intellectual laziness I didn't want to be guilty of. He wasn't objecting because he failed to understand the theory. He understood it better than almost anyone who ever criticized it. He was objecting because he believed, with everything in him, that a final theory of physics should describe a world that exists independently of whether anyone is looking at it. And quantum mechanics, as Bohr had built it, didn't promise that. It promised something stranger, a world that seems to come into sharper focus only in the act of observation itself. What I've thought about more in the years since is that neither of us had the tools to settle it definitively, not in the way you'd want a scientific dispute settled. Einstein believed hidden variables existed somewhere beneath the quantum description, waiting to be uncovered by a smarter theory. Bohr believed there was nothing underneath to find, that the probabilistic description was, in some sense, the deepest layer physics would ever reach. And the honest truth is that, for most of my working life, the argument remained exactly that, an argument, unresolved, brilliant men on both sides, no experiment capable of adjudicating between them. It would be years later, after the war, after Los Alamos, after most of the men in that argument were gone, before physicists worked out ways to actually test the question experimentally to see whether entangled particles behave the way Einstein's hidden variables would predict, or the way Bohr's completeness would predict. I won't pretend I saw that resolution coming during the years Einstein and I debated it face to face. Neither of us did. We were arguing about the deepest structure of reality with the only tools we had at the time: mathematics, intuition, and an argument neither of us was willing to lose gracefully. What I remember most honestly isn't who was right, it's the quality of the disagreement itself. Einstein never once tried to win the argument by appealing to authority, even though he had more of it than almost anyone alive. And I never stopped taking his objections seriously, even when I believed the evidence stood against him, because I understood that the discomfort he felt wasn't a failure of imagination. It was physics doing exactly what physics is supposed to do, refusing to let anyone, however brilliant, settle for an answer just because it was convenient or elegant or easy to accept. We disagreed for years. I'm not sure either of us ever fully let it go.